Hey guys, today I'll be going over a USACO 2021 December silver problem called Connecting Two Barns. It was one of the hardest silver problems they've released. It gets harder every year, so I'll go to my online judge and go right into the problem. I'll teach you guys how to do this one. So Farmer John's field consists of n fields, 1 to n, m bidirected paths, so typical DFS type problem, nothing crazy. The farm contains two barns, one in field 1 and the other one in field n, so we have two barns like this. Way to walk between two barns along some series of paths. So long story short, we have other barns like this. And then we want to somehow connect barn 1 and n and minimize the cost. So let's say n is like 7. Let's say that this is like 2. Right? Then the cost would be 1 to connect this, because 1 squared is 1, and 5 squared is 25. So the total cost would be 26. Same thing, if we connect barns 1 and n, this would be 36. So connecting barns 1 and n wouldn't be optimal in this case. So how do we go about solving this problem? It seems like we can just line all of the connected components up and just somehow do a brute force search, which clearly won't work because anything over O(n) squared will go way over the time limit, because look at our input size. So we have to think of something much more optimal. First thing I want to say is there are a lot of edge cases that you should remove in order to solve this in reasonable time. But actually the fun thing is that all of these edge cases can be removed together. So let's just call this case 1. This is like the edge case. This is when barns 1 and n belong in the same connected component. So they might be directly connected. They might be connected like this, or there might be more connected components here. Doesn't really matter, because all you have to do is DFS1, right? And then we would obviously fill up a visited array. And then if visited n, then you just have to print 0. Simple as that. Why print 0? I mean, it's pretty obvious, but you don't, if 1 and n belong in the same connected component, you don't have to, the cost is 0 because you don't have to make any connections. That's test case 1. Test case 2 is the harder one, and that's why this problem may be a little bit more difficult. This is when, obviously, barn 1 and n don't belong in the same connected component. So how do we solve this? So actually the solution is pretty elegant. So you would have a vector, a sorted vector, that stores all of the connected components in 17 or something like that. And then we would have barn n. We would have like, 3, 11, 20, something like that, right? The first thing we have to do is compare these two, right? So ignore all the other connected components, right? Just focus on comparing. Okay, let's say we have connected components like this. Just focus on comparing the ones that contain 1 n, right? So how would you solve this? Easy. You just have to do a binary search. So you just traverse one of the arrays, traverse this one, vectors, and then for each value, you would conduct the binary search in this vector to find the closest value. So for 7, you'd do a binary search and you'd determine that the closest value is either 3 or 11. It doesn't really matter because you would just store the cost in the min variable. So it would be 4 squared, which is 16, but you would look at 9 and you would do a binary search and you would land on 11. And the cost is 4, because 2 squared. And it happens to be the minimum cost for this combo. So you'd store that in the minimum variable. Just keep an eye on that because, we'll be using this. So I'll just try to erase. Wait, let me make it smaller so we can fit the other ones. Min equals 4. Now we have a bunch of other connected components. So if you couldn't guess, we're just going to make an array of vectors like this. And of course they're going to be sorted because we're going to be conducting a binary search. I don't really want to fill all of these out, but just say we have distinct nodes, or aka the barns. So we would do the same thing. We traverse this, and then for each value, we conduct the binary search for every single vector. For this one, we do the same thing. We do a binary search for every single one, for each vector. And then we would eventually, so if we do a binary search for 1, for all of these connected components, we would get, let's just call it min 2. And then we would, find some kind of min 2 value. it could be like 9. Like let's say distance is 3, so we have 9, and then we compare n and every single connected component, and we might find like a min 3 value of like, I don't know, 16. Then we would compare all 3 of these values, and then we would just print the final min, which would be 4. So that's it. That's the whole logic. We only have to separate it into 2 test cases. It's pretty simple. If it didn't make sense, it's all right. I'll jump into the code and hopefully it makes more sense. So this is my source code. It was a bit shorter than I expected. I'm not sure if anyone solved it my way. I think my code is pretty unique, but anyways, we have the visited array for DFS. We have the adjacent vector. This is just for the DFS, and then group 1 and group n. Remember the 2 vectors that, this is the vector of connected components to barn 1, connected components to barn n, and then this is the vector of vectors. I called it groups, and then this would contain the vectors that represent all of the other connected components, set of connected components that don't include barn 1 and n. And void connect, this is just a DFS. I just called it connect. For all of the test case, number of barns, and this is the number of paths. This is just reset. I like resetting in the beginning of a while loop rather than at the end, because oftentimes I break out of the while loop in the middle and I forget to reset the vectors and arrays properly. And then this is just insertion into the adjacent vectors. You should be familiar with this. And then connect 1 and G1. This is barn 1, and I'm basically conducting a DFS for barn 1. And then group 1, I just take as a parameter because I want to insert all of the values that are connected to barn 1 in group 1, because that's what group 1 represents, right? So I do this, and then if visited n, so if I started the DFS from 1 and then we end up visiting n, that means barns 1 and n are connected, in the case of which we'd print 0. If it's not the case, then we would also have to do a DFS from group n and then insert all of those connected components into group n. And we would sort these 2 vectors for the binary search. And then this is for the other connected components that don't include barns 1 and n. So if it's not visited, of course, we don't want to, because each barn has a unique number, we don't want to insert the same barn into another group of connected barns. So vector int group connect. So it's the same logic as above, but I take this vector, I take it as a reference vector and as a parameter, and make sure to add the AND keyword. Okay, so you're traversing all of the nodes, and if it's not visited, then you'd make a set of connected components, right? You're doing that here. You'd sort them for the binary search, and then you would push back that entire group into the groups of connected components. This should make sense if you saw the previous explanation. And then this is just the binary search. So min1, this is just a binary search. We're traversing group 1, and then we're binary searching each value in group n. And then, okay, this one's actually important. We have min4. I'm going to explain why we have min4. So we're going to traverse the groups vector. We would have min2 and min3. We're traversing the groups vector, so we are currently looking at a group vector. So it would just be the connected components of a certain group. So for each value in that set of connected components, we would look for the closest value in vector group 1. And then we would, for this one, we would look for the closest value in group n. We would store the combination of min2 and min3 in a min value called min4. You need to make sure that these binary searches are being conducted for the same barn you are looking at in the group. Long final min, this is just comparison between our min4 and our min1. So this is the binary search between group 1 and n. This is the binary search between group 1 and all the other groups, and group n and all the other groups, which is stored in min4. So yeah, we output final min, and we would obviously clear everything up. I'll just show you how the binary search works. It's I thought the binary search would be more complicated, but I tried this and it worked. And now I understand why it works, because you just have to conduct a binary search, a normal binary search. And obviously you're going to be using longs because you don't want to have an integer overflow. And then while you're doing the binary search, just constantly calculate the minimum distance value. So obviously I minus j to the power of 2. Oh, you need to add this conditional. I struggled for quite a bit because of this conditional, because you usually don't need this for binary searches. Yeah, but the general idea is that you're just continuing the binary search until you eventually land on a value that yields the minimum distance. So yeah, it's pretty straightforward. The code may be long, but this was the shortest I can make it. My first trial was like 250 lines, so obviously a great improvement here, but good luck with this problem.